Yeah. Okay, a little over, but let's go ahead and get started. 1 second.
Actually, yeah, you were in
There we go. All right. So updates, I'm going to post your homework tonight, and then you'll have, again, until Thursday to do that. Make sure that your homework for today is turned in at the end of class. Unfortunately, I do not have your 3 and 4s back yet. A little behind on that, but I'll have your grades in over the weekend at least, and then I'll give those back to you on Tuesday. Collect, probably have your 5s and 6s back next Thursday. Okay. All right, any quick questions before we keep going? They should be. Are they not? No? Okay. I'll check that on Canvas. All right, anything else? Okay. Well, today we're going to get to exact and inexact equations, and this will be the end of chapter 2 for us. I saved these ones for the end because they're a little bit trickier. But we'll work through the details and hopefully understand what's going on with them. All right, so before we do that, I want to finish off constant coefficients because we didn't do the general solution. Here is the form of the general solution of an equation with constant coefficients. So that looks pretty long. Some ugly stuff in there. There are a couple of things to note about this. So first off, I wrote things in terms of parameters. So you have A, alpha, B, and beta in there. And then H and K you'll find using the method that we talked about last time. But A, alpha, B, and beta are new parameters that maybe you haven't seen before in these problems. And where do they come from? Well, A and B come from partial fraction decomposition. So the general form of the solution for an equation with constant coefficients requires you to integrate a rational function where the denominator is a quadratic. And that's where A and B come from. Alpha and beta come from having to factor the denominator when you do that integration. So one more thing to note is that this isn't generally going to be solvable for X or Y. So depending on what A and B end up being and what alpha and beta end up being, it might be really hard or impossible to get one in terms of the other. There is one case where you can. It's if A is equal to minus B and A is a fraction of the form 1 over m. Because then what you can do is you can multiply by m on both sides. Let's write this down. If this is 1 over m, oh, actually, never mind. And this is 1 over m, then you can multiply both sides by m, and then that ends up in top here. And then you can combine these the form log absolute value thing over thing. And then you can cancel out the logs and solve for y. Let me check. Should be. Yep, it's on here. Yes. Is it on? Really? Okay, give me 1 second here. Oh, I might have forgotten to do something here. 1 second. Yep, got it. All right, thanks for letting me know about that. Let's pull this back up. All right, is this better? Yeah, better, no echoing. All right, good. Okay. Okay, so we were just saying that you can do this if you have these conditions, and then this will allow you to cancel out the logs and then hopefully solve for y. It might be a little tricky and take some annoying algebra, but it should be doable in that case. Otherwise, I want you to think, leave it like that. Okay, so let's quickly run through how you would get that, just so we're familiar with the method that we talked about yesterday that we saw with examples, but we didn't really see as a formula. So we start with an equation of the form dy dx equals ax plus by plus c over dx plus ey plus f. And remember, our goal was to choose h and k to cancel out c and f. So remember, we did this. All right, and then, well, we remember from last time that we figured out dv du is always equal to dy dx. And I mentioned a shortcut in the last problem that upon substituting, h and k don't show up, and you end up with, well, exactly what you wanted. Right? So you can start from here and find h and k later. And then we go through and we do our substitution for a homogeneous equation, which is this one. W equals b over u, which gave us, let's move that up, a derivative of v w plus u dw du. Okay. And then plugging this in here, we have w plus u dw du equals a plus bw over d plus ew. All right. And we can move the w to the other side and find a common denominator. This should be somewhat familiar. And if we add those together, we get dw du equals a plus b, some space here, b minus d w minus e w squared, divide by d plus e w. All right, and now this is separable, which is the point of our homogeneous substitution. So we can rewrite it as d plus e w over a plus b minus d w minus e w squared. Okay. And then dw equals du over u. All right, so once we're here, now we want to find the antiderivatives of both sides, and we'll call it a day after back substituting. But we got to deal with that ugly looking left side. So the right side is pretty easy. Log absolute value of u plus c equals the antiderivative of this horrible thing. And what is this horrible thing? Well, it's a thing that we're going to turn into a partial fractions like object. So before I write that down, I'm going to note that there's an e right there, and I don't love leading coefficients that aren't 1. So we can factor it out and have 1 over e right there. And that leaves us with a tilde plus b tilde, which is a little silly named, but I don't want to have to write a whole bunch of stuff there. And then minus w squared dw. All right. At this point, I need to factor this so that I can do partial fractions. There is another way to do this, but it will be a little bit tedious with the parameters in there, the arbitrary ones. So what we want here is now to factor this. And when I do this solution, or when I'm actually doing this for a specific problem, I will have the numbers written out here, and I can figure that out whenever I want. So what we're going to do in general here is just say, all right, well, this will factor as something that looks like this. Yes. And you can double check that. So it'll factor as something that looks like that. And then we can work through with those new parameters and find a solution in terms of them. So we have, finally, well, u plus c equals 1 over e d plus ew over a tilde plus b tilde w minus w squared dw. Okay, so that's what we'll carry with us to the next page. So we have this, and I wanted the factored form, sorry. Alpha minus w beta plus w, that's what I wanted there. All right, so now we guess our partial fractions decomposition. And again, A and B are parameters that we have to use a completely different process to find. That doesn't affect the integration here at all. They're just numbers at the end of the day. And so we can integrate this with respect to W. Okay. Yeah, we'll leave it like that. That's fine. Okay, so we have 1 over e here. And now, if we integrate this, here, you want to do a substitution if you need to. Say t equals alpha minus w, but I'll just write down what we get. Minus a log alpha minus w plus b log beta plus W. Okay. And so this 1 over E is here because I forgot to absorb it into this part, but that's fine. All right. And more or less, there's our solution. Okay. So we took the process that we figured out through examples and did it in general. And because it was pretty nasty, we made some simplifying assumptions, right? That we don't have to find A and B in general. We don't have to find alpha and beta in general. It will make this formula nastier than it has to be. And we can find H and K later on. Question? Yes. So we can find H and K next. And that part is the last thing we'll do for finding the general solution. We good? Okay. All right, so last is finding H and K. And then that comes from our differential equation, ax plus by plus c over dx plus ey plus f. And maybe you remember that the system of equations that you have to solve ends up being exactly ah plus bk plus c equals 0, and dh plus ek plus f equals 0. Okay. And this is a lot of letters. So what I'm going to do is walk us through the matrix method of solving this. So we can write this as A, B, D, E, right there, and then H, K. And this is equal to minus C minus F. And it turns out that for inverting a matrix, so if you think of this like an equation of the form 3x equals 2, how do you solve this for x? You divide by 3, right? You can also think of that as multiplying by the inverse of 3. And that's what we're going to do here. So we have something that looks like this, and we're going to solve it by finding a thing that turns this into 1. Okay? And it turns out that that thing is this formula. E minus B minus D A. Okay. So our solution for H and K is going to be that formula times, not HK, minus C minus F. Okay. And so when we go ahead and multiply all of that out using your matrix multiplication, we get that H is minus CE plus BF over AE minus BD. And K ends up being CD minus AF over AE minus BD. And those are your general solutions for H. So we take this to the other side, and we use this to find the solution of this example. So I'm not going to ask you to do this. I'll write it down for you. Let's find h and k first. And then we have to identify what A, B, C, D, E, and F are, right? So you can maybe write those above the numbers. So let's see, we'll have, maybe we should just rewrite the whole thing. dy dx equals, well, we'll have x plus 3y plus 5 in the denominator. And then in the numerator, we'll have the negative of this, because we have to subtract it over to the other side. So minus 2x minus, or plus 2y plus 6. Okay, so we've got a equal minus 2, b equal 2, c equal 6, d equal 1, e equal 3, and f equal 5. If we plug those all in here, we've got minus 6 times 3 plus 2 times 5 over minus 2 times 3 minus 2 times 1. All right, so that's minus 18. This is plus 10, minus 6, minus 2. Okay, so minus 18 plus 10 is minus 8 over minus 8. And so we get 1 for h. All right, again, c, 6 times 1 minus negative 2 times 5 over a is negative 2 times 3 minus 2 times 1. Oh, look, the bottom stayed the same. So we know we're going to get minus 8 there. And then in the numerator, we've got 6 plus 10 is 16. So we get minus 2. All right. So h equals 1, k equal minus 2. And we can take these over here and write down our solution, which is going to be natural log absolute value x minus h plus c equal minus a log absolute value, this alpha thing, minus y minus k over x minus h plus b log beta minus y minus k over x minus h. All right, so plugging that stuff in, we get log x minus 1 and then y plus 2 over x minus 1 plus b y plus 2 over x minus 1. And I think I have the parameters for those ones now. No, I have that for a different one. Okay, so from here, go back and find A, alpha, B, beta. So you want to find alpha and beta first. I'm not going to actually work through this. I'll just tell you what to do. And those will be the roots of this equation. For W. And then A, B will come from D plus EW over A plus B minus D W. Forgot my over E. Over E. W minus W squared. A over alpha minus W. B over beta plus W. And once you have alpha beta, you don't have to write all of that. You can write alpha minus W beta plus W there. So that's why I say find alpha and beta first, then you can find A and B because they're important for finding A and B. Okay. So that's the end of equations with constant coefficients. Any quick questions about this? I'm not going to ask you to recreate this, but I want you to see how to work through things in general when they might look ugly, because things might end up being very, very ugly later on. It's good to get practice now. Sure.
With like the matrices,
Mhm.
like what if we're not like really familiar with that? How would we go along?
So you know how to do substitution for linear systems? You can do that.
Okay.
Yeah. And again, I'm not going to ask you to do this in general with the nasty parameters in there. And so what you'll end up with is a system of equations that looks like this, and that you should be able to solve relatively easily. Mhm. All right. So, did you need to see slide? Okay. All right. So now we'll talk about exact and inexact equations. What are exact and inexact equations? So we know that some differential equations have solutions that you can't solve for one variable or the other. And some you're forced to solve for X instead of Y. This happens a lot. Sometimes differential equations are just really nasty. But in a few cases, again, a class of differential equations, we can find solutions that are level curves of some two variable function. And so what is a level curve? A level curve is you have some two variable function and you say this is equal to some constant. Right? So it's all of the points x, y in the xy plane where f of xy is maybe equal to 2. And then maybe here you have f of xy equal to 1. And then maybe out here you have f of xy equal 3. So it's kind of like a topographical map, if you've ever seen those while hiking, or maybe looking at a map on Google Earth or something. That's basically what this is. It just tells you where is the height 1, where is the height 2, and where is the height 3, and so on. And so that's what we're going to get as a solution in these problems. So we need a definition. So an expression of this form, or we saw that with the previous type of differential equation. This is called a differential one form, and it's in two variables, x and y. And we want all of our exact equations to be written looking like this. So a differential equation is called exact if it can be written as a differential form like this, equal to 0, so that there is some function f, two variable function, spits out real numbers, with the derivative with respect to x equal to m, and the derivative with respect to y equal to n. Basically, you want this and this to be the derivatives of a single function. If you can't find such a thing, then the equation is inexact. And that can happen. We'll see some examples. All right, so I'll go back to that in a second, but we'll start with some practice. Decide whether these are exact or inexact. I'll let you write these down, and then in a minute, I'll go back to the previous page so you can check. So you know what to check. Anybody still writing these down? So I'll go back to the previous page now, and you see if you can use that definition to figure out whether those differential equations, those differential forms, are exact or not. Just means that there has to be some function f whose derivative is the dx part and whose y derivative is the dy part.
He's gonna be his default.
Sorry.
But 10% mistake. See, that's amazing money.
Oh, why? Are you like 7 to 8 hours? I know that. Oh, no, but if you're used to always. I think I get tired.
It's somewhere around here. Does someone have the attendance?
You're not crossing off on. That's what I said. I get 50-50 chance. Actually, you have like a what?
This part should be hard.
Yeah.
Yeah. All right. Let's give this a shot. So, anyone have a guess for A? Exact. It is exact. Anyone have a guess for B? It is inexact. Yes. Okay. So cool. We know the answers. How do we get those? Directly. So A, you have to rewrite, right? So you have to write it in the.
Is it because the function derivative of the 2x squared and 2x squared y is the same?
Ah, yes. But we're not going to do that just yet. We'll do that right after this. Did I give myself? Yeah, I gave myself enough space here. So let's rewrite A first. We have, okay, if you rewrite this, it will look like this as a differential form. 0. Okay, so given that, now we need to know, is this, or are these two things true simultaneously? Can they be? Okay. Well, if this we got from taking the derivative with respect to x, then we can undo that derivative with respect to x. So integral dx here, and we get, well, okay, 2x x squared y squared. Okay, antiderivative of 1 with respect to x is 1, and then plus c, right? Almost. So because there are two variables involved now, that could be a function of y. Because if we take the derivative with respect to x, we're ignoring all of the y's, right? We're pretending that they're constants like 2 or 3. And so if you have an added part that's just a function of y, if I take the derivative with respect to x of this, I get 0 out because it's like differentiating 2 or 3. All right. So if that's the case, then this one also gives us something. It says f equals x squared y squared plus maybe some function of x. We can use either of these to get a solution. Let's go ahead and use this one. So now the last thing that we need to know is if this is f, does it satisfy that? So we can check by taking the partial derivative of this guy with respect to y. All right, so if I take the derivative with respect to y now, treat x like a constant. That's a constant. This is not a constant now. So if x is a constant in the first term, we should get 2x squared y, good sign. If x is a constant in the second term, we get 0. That just goes away. And then, g is a function of y, so this should be g prime of y. Or maybe I'll write with Leibniz to be consistent. We'll write d, g, dy. And I'm just writing a non-curly d there to emphasize that g is a function of one variable. So this has to equal 2x squared y. Can I solve this differential equation? Sure can. So the 2x squared y's cancel out, right? And then the 0 just goes away. So we have a really easy differential equation. dg dy equals 0. Can you solve that for me? Almost. Not necessarily 1, but not y. What has a derivative of 0? A number, yes. You're 1 power off. So yes, g of y equals some constant c. And that works. That differential equation had a solution. So we get f of xy equals x squared y squared plus x plus c, and this should be equal to 0. Okay. And if you rearrange things, you can write x squared y squared plus x equals c. Okay, this one looks solvable for y. That's not going to happen every time. At the very least, when we solve this one for y, we'll have to do a plus minus for that square root. In a lot of other cases, you won't even be able to do that. So let's just check the last one, make sure that we can tell why that's inexact, or we see maybe an idea for why it's inexact. We have 1 over y, and then minus 3y minus x over y squared. So 1 over y dx minus 3y minus x over y squared. Okay, so if we try the same thing, then this tells us f should be, right? That's like taking the antiderivative of 1 or 2, right? X over y plus some function of y here. And now I take the derivative of this with respect to y. Right, and I get, let's see, minus x over y squared. plus dg dy, and that has to equal minus 3y plus x over y squared. And what happens if I solve this for dg dy? I get an equation that looks like 2x over y squared minus 3y. What is the problem with the right side there? Maybe give me a guess. What do you think might be the problem with the right side? The 2x, exactly. Yeah, you're not supposed to have any x's on that side because g was only supposed to be a function of y. So if you end up with an x on this side, something went wrong. That tells you that this differential equation is inexact. G is a function of only y. So this is inexact. Okay. So what do we do? That was kind of annoying. I don't want to have to integrate and then take derivatives over and over again and try and equate things, solve other differential equations. It's a hard process. So what can I do to check if something is exact without doing that? Well, I can do this. I can say, all right, well, if these functions are continuous, and let's go back for a second. This is continuous, this is continuous, this and this are almost everywhere continuous. Just y equals 0 is a problem. And exact in a simply connected region, this just means away from like that y equals 0 place. So simply connected means something that looks like that. Something that is not simply connected might look like this. Right. So if those guys are continuous on some blob, and these two have derivatives in opposite directions that are equal. So what is this really saying? So if m and n are exact, then df dx equals m and df dy equals n. So that was the definition. We needed that for an equation to be exact. If we now take the derivative with respect to y of this one, we're saying that the second derivative of f should be equal to dn dx. Now the second derivative of f with respect to x after y. So we're saying that it shouldn't matter which direction you take the derivatives in. You take either x or y first, and you get the same thing out. And that is a good enough condition to get exactness. Okay. So how does this work in practice? Do we have any quick questions? We haven't started doing anything big yet. Okay. Practice. See if you can use theorem 2 to decide whether the following differential forms are exact or inexact. And I did not want a 0 there. So just check if the forms are exact or inexact. I like that energy. All right. So we have an answer. Is A exact?
Yes.
Yes, it is. Is B exact?
No.
No, it is not. Are these the same differential equation if I erase the red part? Yeah. So the problem here is that exactness is not really something that we can say about a differential equation without being a little bit more specific, but we can say it about the differential form, just the left side of the equation. So the same differential equation can be written in exact or inexact forms. All right, so yes, exact and inexact. Okay. I think we can skip that part. So what do we do? If we have an exact equation, how do we find a solution? So here's an example. We'll work through this one together. First off, we want to verify that this actually is exact. So let's say, all right, we want to take this thing and take its derivative with respect to the opposite variable. So with respect to y. So dy 2x squared y minus secant squared x equals, this is constant, so it goes away. And then the only part we care about here is that y. So we get 2x squared. All right, now if we take the derivative with respect to x of the other part, x squared plus 2y, all right, well, that part goes away. It doesn't depend on x. And the other part does depend on x with derivative 2x squared. That shouldn't have happened. Let's think for a second. What did I do wrong? Oh, my bad. That 2 wasn't supposed to be there. All right. So there we go. Now it's exact. Okay. So this is exact, and we want a solution in the form of some function of 2 variables set equal to a number. What do we do? Well, unfortunately, we do what we did the first time. We say, all right, now we know that it is exact, and so we don't have to waste our time trying to find a function f when there might not be one. So basically all we've done is say, all right, we found a way to solve it before the first time, and sometimes that didn't work. Now we know when it does and doesn't work, and so we can not waste our time by checking if it doesn't work ahead of time. So let's see, we've got 2xy squared minus secant squared x, and this is supposed to be equal to the derivative with respect to x of something. Okay, Well, I can find the antiderivative of that. 2x gives me x squared, y squared, and then secant squared is the derivative of what? Tangent. So tangent of x, and then don't forget right here, when we're doing exact and inexact equations, we've got two variables. The constant here needs to be a function of y. Okay. Then take this thing and take its derivative with respect to the other variable. So we undo a derivative and then we do a derivative in the other direction. All right, that gives us 2x squared y. This part goes away. And then we get plus dg dy. All right, and what does that have to be equal to? Let's see, it was 2x squared y. Oh no, x squared plus 2y. Did I do that right? What did I do wrong? X squared plus 2y. Antiderivative. Oh, I keep writing the y squared there. All right, that shouldn't be there. There we go. And then, yeah, okay. Sorry, that's my mistake. So we should have x squared. Yeah. All right. Now the x squareds cancel out. And just again, another check. Is this a differential equation only involving g and y? Yeah, it is. There's no x left over. It cancels out. And that's what should happen when the differential equation is exact. All right, we go ahead and solve that. It's a separable equation. dg equals 2y dy. So g equals y squared. All right, and then that gives us our solution. Y squared plus c. You don't have to write that, because we know that we're just going to add it to the other side of this equation. Plus y squared equals c. And that's our solution. If you want to, you can also try starting with the other side and seeing how things shake out. So see if you can do the same process starting from the derivative with respect to y. I'm not going to have you do that now. You can do that at home if you want. All right. Give myself more space. So how do we do this in general? Well, you've seen the idea already. I just wanted to write it out. So we have 5 steps here. So this is starting from this side. So write that this is the derivative of something and integrate both sides. So this is that first part. Once we know we have an exact thing, just take the antiderivative of one of the m or n. And then remember to put g of y there. Right. Then take the derivative with respect to y on both sides. So we get this differential equation down here. So this was that part, and then you take the derivative with respect to y of both terms and say that has to equal n. All right, now you can solve this for G. If it's exact, all of the X parts should go away. And then you just add whatever you get for G back in up here, and that's your solution. And you say, all right, that's equal to some constant. Okay. Sure. Mm-hmm. So we have questions about this process. Let me give you a practice example here. Give you a couple minutes to work that out, and then we'll come back and find the solution. Doing it from both sides just adds time.
I'll just go and think about it. I've already run that.
Yeah, no, I thought I'll run it, and then I was like, I won't run it.
No.
No, it's like just knock off.
It's actually like.
But
Everybody color green. Bro, about to get.
I don't need it. I'm definitely gonna roll that song. We do a party.
All right. How are we doing? Close to a solution or still towards the beginning? No? Not close? Okay. So let's take what you've got and work through this now. So we want this side to be the x derivative of something and this side to be the y derivative of something else, or the same thing. All right, so if we have df dx, and by the way, I'm giving you that this is exact. You don't have to check it here. Is 2xy plus 3. I take an x antiderivative and I get x squared y plus 3x plus g of y. All right. Then I take the y derivative and I get, well, let's see. This part goes away and I get x squared plus g prime equals x squared minus 1. The x squared part cancels out, and I get an easy enough to undo derivative. Tells me g is equal to minus y. And then my final answer is x squared y plus 3x minus y equals some constant. And then we're done. And that's how you solve exact differential equations. What happens when things are inexact? You don't solve them? Sure. Yep, you should get the same answer. Okay. All right. I know we're almost done. Give me 5 more minutes of your time. All right, so what happens when things are inexact? You take this form and you take their derivatives and it doesn't work out. They're not equal. So the exactness can depend on how things are written, right? If we multiplied, or if we wrote that other example in one way versus the other, it might not be exact. So you can actually exploit that. Theorem 2 is what we can use, and we'll use your favorite buddy, the integrating factor. So multiply by something here that hopefully makes the exactness condition work. And for obvious reasons, this thing's called an exactifying factor. All right. So how does this work? Well, we'll probably only get through this example and then that'll be it. I'll put the general part in the slides later. But I want to find some function mu that I can multiply in here. And notice on the right side, it's 0 times mu, so I just get 0. So that the derivative of the first part with respect to y equals the derivative of the second part with respect to x. Okay, and so what do we do here? Well, I'm gonna have to use some product rule. So product rule on the left side, mu is a function of y. We'll think d mu dy times 2xy plus mu times the derivative of the other part with respect to y. It's 2x. All right. And then here, d mu dx times y squared minus 3x squared plus mu times the derivative here with respect to x. The y squared part goes away. And we get minus 6x there. What kind of differential equation is this? It's a differential kind. Is it an ordinary differential equation? No. What kind is it? Extraordinary. We call those partial differential equations because there's 2 variables involved, right? So that's a problem. That's a whole different class. This is now not something that you know how to solve yet. So what do we do instead? Don't put it on your test. So don't put on test. Yeah. No, what we do instead is we make an assumption. Mu of xy is really just going to be a function of x. And this will make our lives a little bit easier. Why? Because now d mu dy is equal to what? if this function only depends on x and I take a y derivative, I get 0. Okay, so then if I come back over here, that whole term goes away. And now I can rewrite my differential equation as an ordinary differential equation. All right, and so this will be 2x mu d mu dx, regular derivative now. And this part right here should be minus 6x mu. Okay. So now you can go ahead and hopefully solve this for mu and try to find a solution. So let's write down what that is real quick, and then I'll let you go. So d mu dx equals something over y squared minus 3x squared over, or under 8x mu. And looks like we might have a problem here. This depends on y still. So the assumption that this thing depends only on x doesn't work. Instead, try this. That will work. Okay. So what you should end up with down here is a differential equation that only involves the variable that you're trying, or that you're assuming is mu is dependent on. Okay, we'll stop here, and then we'll talk about some modeling stuff next time. Make sure that you turn in your homework. Thank you.
And then, where does this x squared come from? The integral of this?
Sure. Have a good weekend.
Because that's what we did to the
Probably.
the cancer here.
If you're turning in your homework, you can just come up here. What?
Oh, that just check for you.
Oh, this is check.
I'll get the x squared y plus 3x plus g of y.
Oh, it comes from here. Okay, so you take the y derivative of this. So that would be x.
All right, thanks. Quick question.
Yeah.
I can't find the online like video lectures.
It's because I haven't been posted. It's taking me forever to get those edited. But I think the first few will probably go up this weekend. And I know it's late, but I'll get them up faster and faster as I go.
Okay. Also, what's your email address? Because like, is it the one on the syllabus?
Yes.
I've been emailing and I
Yeah?
haven't had a response yet. Is it because I think you have the at uncc.edu.